So last time we were talking about limits at infinity. So I want you to kind of pay attention to this word right here, at infinity. So here we're given these two limits, the limit of 1 over x as x goes to infinity, and the limit of 1 over x as x goes to negative infinity. So up until this point, we have not done a limit like this, where we're sending x to infinity. That's what we mean by limits at infinity. Here, we're wondering what happens to the function when you send the input variable to infinity or negative infinity. So that would be the first thing, to notice about these limits that are different, is that these limits, we're sending the input variable to infinity, and we haven't done that before. So we started to look at this limit last time. So plugging in points as x goes to infinity, we see that when you make the denominator bigger and bigger and the numerator is a fixed constant, what happens is the fraction gets smaller and smaller. So here, 1 over x as x goes to infinity, that limit goes to 0. And similarly, if we send x to negative infinity, we have same type of pattern. If you fix the numerator, if you let the numerator be a fixed constant and let the denominator get larger and larger, we see the fraction gets smaller and smaller and goes to 0 or converges to 0. So essentially, based on these numerical experiments, we come to these two conclusions, that the limit of 1 over x as x goes to infinity equals 0. And when I say that, what I mean is, in the numerator, when you have a fixed constant, and in the denominator, when the denominator is blowing up to infinity, this experiment is showing the limit goes to 0. And same thing, if we have a constant in the numerator, and in the denominator, we're allowing the denominator to blow up to negative infinity, the experiment above shows the limit goes to 0. So these two limits lead us to a new limit rule. So remember, our first rule for limits, once we recognize it's a limit, is to try and plug the limit in. So here, for example, with this problem, if I try and plug infinity in, I get quote unquote 1 over infinity. Remember, this is not math. So here, when I write 1 over infinity, be very careful. That's not math. It's just some symbols that are allowing me to analyze the situation. So when I get 1 over infinity, this is exactly the number over infinity in a limit scenario. And so these experiments tell us number over infinity in a limit is going to give us, the limit's going to equal 0. And so this is kind of our, a new limit rule now that we want to keep in mind. That in a limit, if you get number over infinity, that limit is going to be 0. Of course, the 1 over x graph is a great graph to remember because it kind of has all that information built right into the graph. And here, when we're sending x to infinity, we're looking at the tail behavior here. What's happening as x goes to infinity and as x goes to minus infinity. So before I do an example, let me give you a definition of a horizontal asymptote, because we use these limits at infinity to find horizontal asymptotes. So the limits at infinity is very connected to the concept of a horizontal asymptote. So we say the horizontal line y equal to L, where L is a real number. Remember, this notation here means L is a real number. So the horizontal line y equal to L is said to be a horizontal asymptote of the function f of x, if and only if either the limit as x goes to infinity is some finite number L, or the limit as x goes to negative infinity is some finite number L. Here, to find a horizontal asymptote, we need to check these two limits, x going to infinity and x going to negative infinity. If the limit exists, that is, if the limit's a finite number in either direction, then we have a horizontal asymptote. And here, it is possible for a function to have two different horizontal asymptotes. Okay, I'll do an example shortly where I'll show you a function where when we take the limit as x going to infinity, we get one answer, but then when we take the limit of the same function as x goes to negative infinity, we get a different answer, okay? So I'll show you an example of that in just 1 second. So here, let's first do this example. So this is a limit at infinity example. So here I'm taking a limit of the function sine x over x as x goes to infinity. So I want you to be really careful. We learned a special limit. This is not the limit of sine of x over x as x goes to 0. I do not have a 0 down here. This is the limit we've been studying. The limit of sine of x over x as x goes to 0 is 0 over 0. But if we use a squeeze theorem, we can show this is equal to 1. And this is one of those limits, I've asked you to memorize. But here, this is not that problem. So I want you to be really careful here and notice this is a limit as x goes to infinity, not as x goes to 0. So I can't just say this equals 1. So here, the limit is an indeterminate form. So remember this phrase here, this is for forms and limits where we don't know what's happening. And here, this is an indeterminate form because the numerator, the limit of the numerator as x goes to infinity does not exist. So when x goes to infinity, we're not sure what's going on up here. Because if you think about the sine graph, when we send x to infinity, sine just oscillates forever. So technically that graph in the limit in the numerator doesn't exist. So the whole thing is weird because of this numerator issue. So having said that, the trick to doing this limit is to use a squeeze theorem. And here, because x is going to infinity, I can assume x is greater than 0. That'll come up when we try to manipulate the inequality. So for squeeze theorem, I need an inequality. Here we have an easy place to start. We know that sine of x, this function here in the numerator, is always bound between -1 and 1. So that's an easy place. Anytime you see these limits involving a trig function, especially sine or cosine, if you're going to do a squeeze theorem, there's always a nice place to start because sine and cosine are bounded functions. So now I want the sine of x to look like sine over x. So now I'm going to divide by x. And here's the part where I said, since x goes to infinity, x is greater than 0. Since x is greater than 0, when I divide by x, it doesn't change the direction of the inequalities. And now we're ready to do a squeeze theorem. So squeeze theorem, among other things, squeeze theorem says if we have these functions satisfy an inequality, then the limit of the functions satisfy the inequality. So here, all I've done is I've added a limit as x goes to infinity to match the problem. Now, as you know, if these limits at the end, at the left and the right, if these go to the same number, then by squeeze theorem, we can conclude the limit in between, is squeezed and goes to the same value. And so now we can use our result here. So for example, for this limit here, if we just try and apply the limit, plug in the infinity. When I plug in the infinity, in limit, I get -1 over infinity. And our rule is, in a limit, if you get a finite number over infinity or minus infinity, the limit is 0. Same thing with this limit. Plug in the infinity, you get 1 over infinity. And be careful, when you write down 1 over infinity, you should really be careful where you're writing at. That's not actually math. Because infinity isn't a number. Infinity is a behavior. Remember that. Infinity is the behavior of getting larger and larger and larger. Negative infinity is the behavior of getting, larger and larger in the negative direction. So number over infinity is 0. So that's why, again, now we get this limit is 0. So here, both limits at the ends here go to 0. So by squeeze theorem, this limit in the middle is squeezed, and so it must also go to 0. And in this case, not only have we concluded the limit of sine of x over x as x goes to infinity equals 0, we've also concluded that, given the definition above for horizontal asymptote, here we can also now make the statement, make the claim that y equal to 0 is a horizontal asymptote of sine of x over x. That's because of this limit. Okay, so that, I did this example for 2 reasons. One is to make you aware of the sine of x over x thing. Like I said, a lot of students will see the sine of x over x, and they'll see a limit, and they'll immediately say this is equal to 1. And that's only true if x is going to 0, and here x is not going to 0. So that's the thing. I want you to be really careful about that. Really pay attention to the limit and what's going on. We can't do math on autopilot. That's when mistakes happen. We have to pay attention to every detail. That's why math is a discipline in my mind. It's really, you have to be on top of it at every step. So I want to do these 3 examples involving rational functions. So these limits, when we go to infinity involving rational functions, we have a special technique that we use. So here, this is a limit going to infinity, and the function is a rational function. It's a fraction of polynomials. So I want to show you there's a specific technique we use, and then there's a shortcut of that technique. So I want to show you the technique as well as the shortcut. So for this limit, as x goes to infinity of the rational function 2x squared plus x minus 1 over negative x squared plus 1, the first thing I would say is when you're dealing with a polynomial, and when we're sending x to infinity, when we're making x very large to infinity or negative infinity, the only term that matters is the highest degree term. So here the 2x squared in the numerator and the negative x squared are really the only terms that matter. Because, for example, if x is 1,000,000, 1,000,000 is a lot smaller than 1,000,000 squared. If x is 1,000,000,000, then 1,000,000,000 is actually a whole lot smaller than 1,000,000,000 squared. So when we're making x very large, so be careful, this is only for the case where x is going to infinity or negative infinity. The largest degree terms are the important ones. So here, when I send x to infinity, the 2x squared goes to infinity. In the denominator, the negative x squared goes to negative infinity. This is a infinity over minus infinity type indeterminate form, or infinity over infinity. Remember our 3 indeterminate forms: 0 over 0, infinity over infinity, and infinity minus infinity, which I'll talk about a little bit later here today. So this is an infinity over infinity indeterminate form. Usually our strategies are factor and cancel, multiply by the conjugate, maybe squeeze theorem if that seems appropriate. In this particular case, when it's a rational function, a fraction of polynomials, the strategy we like to use is to factor out the highest term in the numerator and denominator, and then simplify, and then try to do the limit. Okay, so let me show you this strategy, and then I'll show you a shortcut of this strategy. Okay, so here in particular in this problem, so here we've got our limit as x goes to infinity. I'm mainly concerned as x goes to infinity, I'm mainly concerned with these. So if you send x to infinity, you get infinity over negative infinity, or whatever. It's an infinity over infinity type indeterminate form. So now, because this is a rational function, and x is going to infinity, I'm gonna use the strategy of factoring out the highest order term. So in the numerator, I factored out an x squared. In the denominator, I factored out an x squared. Here are those x squareds. And remember, when you factor out, what you're doing is you're dividing each term by the thing that we factored out. So 2x squared divided by 2x squared is 2. X divided by x squared is right here. And then the last term is a -1 divided by x squared is right here. And again, in the denominator, minus x squared divided by x squared is -1. And the +1 divided by x squared is right there. And so now we're going to just do some algebra. You know, I can cancel terms here, and I can actually simplify this. So when I do that, cancel, cancel, the x over x squared I simplified as 1 over x. And now we send the limit. Now take the limit to finish the problem. So look at what happens. The 1 over x, as x goes to infinity, so the numerator is fixed, the denominator is blowing up, so 1 over x goes to 0. So this will go to 0. 1 over x squared, same thing. Numerator's fixed, denominator's blowing up, 1 over x squared goes to 0. And in the denominator also, this 1 over x squared will go to 0. So at the end of the day here, after applying this limit, all we're left with is, so this one goes to 0. So yeah, after applying the limit in the numerator, all I have is 2 plus 0 over -1 plus 0, right? All these terms here, these fractional terms, they all essentially vanished to 0. Just left with, you know, the 2 over the -1. So that's where this -2 is coming from. All right. So let's do so there's a shortcut we can use. And so Sal says the answer is -2. So let me show you the shortcut. Okay. So you can, here's the shortcut, folks. But you know, the thing about a shortcut is it's really important that we understand the information that we are shortcutting. I do not want to reduce math to just memorizing a bunch of steps. You know, that'll get us through Calc 1 and Calc 2, but then Calc 3, differential equations, matrix methods, numerical analysis, Fourier series. When you get to those higher levels, it's a lot harder if you just try to brute force memorize your way through it by learning the steps, okay? So here's the dominance of powers idea. That, as I said, when x is going to infinity or minus infinity for a polynomial, it's only the highest degree terms that matter. So doing this with dominance of powers, so there's a lot of steps going on here. I'm noticing that this is a limit problem. I'm noticing that x is being sent to infinity, and I'm noticing that these are rational functions. And so then I can use dominance of powers. So what does dominance of powers basically say? In the numerator here, we can ignore everything other than the highest order term. So I'm ignoring, you know, the plus x and the -1. The only term I care about is the x squared. Again, in the denominator, I can ignore anything that's not the highest order term. So I'm ignoring the +1. And so now we've got this new problem, and now I'm just doing this limit here. And first we simplify. You can see the x squared. I can cancel x squared, cancel x squared. And now when we take the limit, you see the limit is -2. You know, identical to our answer here. So this shortcut that I just used is called dominance of powers. This shortcut that I just used. And the idea is that in a limit where x is going to plus or minus infinity, where it's a limit of polynomials, they're being dominated by the highest power terms, hence the dominance of powers idea. And so certainly you're allowed to use the shortcut, and you can use the shortcut on a test. But what I really want you to first understand is what you are shortcutting. It's really important that you first, you know, so the first couple of times I would recommend, for the sake of learning it, that you do it this kind of long way rather than just saying, oh, we can ignore all this stuff And now just compare these two. Oh, look, the x squared cancels, the limit's -2. Certainly that's valid, but I first want you to understand the math you are shortcutting. So here, let me do the second example. In the first example, the highest order in the numerator and the highest order in the denominator were the same. In this example, the highest order in the numerator is less than the highest order in the denominator. Okay, so I want you to see what happens. And here, also keep in mind, x is going to infinity. Oh, by the way, in the previous problem, I should make two comments. Here, when we get this limit, we can now conclude, so we now know that y equals -2 is a horizontal asymptote of this function, of this rational function, 2x squared plus x minus 1 over -x squared plus 1. So right away, once we get that this limit exists, that this limit equals a finite number, we can write down the horizontal line y equals -2. I do not want to write just -2 is a horizontal asymptote. That is incorrect. Just -2 by itself is a number. The horizontal asymptote is a line. So I need to give the equation of the line. So here I want to say y equal to -2 is a horizontal asymptote. The other thing I want you to notice, in this example, if we sent x to -infinity, nothing would change. We would do the same steps. And here at the end, if I was sending x to -infinity, these terms, the 1 over x squared, the 1 over x in the numerator, the 1 over x in the denominator, all these terms still go to 0 if this is x going to -infinity. So for this problem, the limit of this function as x goes to -infinity is also -2. So in this case, it has the same horizontal asymptote, whether you go to infinity or -infinity, but that's not always the case. Okay, I'll do an example in 1 second where that's not going to be true. So for this next example, again, I'm plugging in the infinity just in the highest order terms, because these are polynomials, and for large x, the highest degree term controls the polynomial. And so I get -infinity over infinity when I do that. And so I know I need to do more math. When you get 0 over 0, infinity over infinity, infinity minus infinity in a limit, that's just feedback to you, the user, that we need to do more math. We need to use some kind of other math strategy. We need to use more analysis. In this specific case, involving, quotient of polynomials, I'm going to factor out the highest degree term in the numerator, which is an x, and I'm going to factor out the highest degree term in the denominator, which is an x squared. And then I'm going to, once you factor out the common terms, the numerator and denominator, do the algebra. So here we can cancel one of the x upstairs and one of the x's downstairs. So here I still have an x in the denominator after canceling. So now let's do the limit, and let's look very carefully, see what happens. This 1 over x right here, as x goes to infinity, this 1 over x goes to 0 because the numerator is fixed and the denominator is blowing up. So the entire numerator is going to -2. We have -2 plus 0. In the denominator, the 2 over x squared is going to 0. 1 minus 2 over x squared is going to 1. But then we're multiplying. So here it's really important. You see, this is multiplying. Here, this is going to infinity and we're multiplying. So what's happening is the entire denominator is going to infinity. In the numerator is going to this fixed constant. The denominator is blowing up to infinity. Constant over infinity in a limit is 0. So these terms right here, this term and this term, they go to 0. So it's almost like they've disappeared. So if we just take them out, these terms go to 0. So I have a constant on top, basically just -2. Here, let me get rid of this canceled term. So -2 downstairs, upstairs. And in the denominator, this x is going to infinity. Times 1. The times 1, again, is inconsequential here. I can even remove that if you want. You basically have 2 over x. The x is going to infinity, so our limit, is 0. Let me do exactly the same problem using our shortcut. Okay? So using dominance of powers. So I notice this is a limit problem. I notice it's a limit as x goes to infinity. And I notice it's a rational function. So all I care about are the highest degree term in the numerator and denominator. So in the numerator, I can forget about the +1. In the denominator, I can forget about the -2. Now do some algebra. Here in the numerator, I can cancel the x. In the denominator, I can cancel one of the x's. Now apply the limit, right? As we send x to infinity, this x in the denominator blows up to infinity, and I have a constant in the numerator. So the entire limit is, fixed constant over infinity, number over infinity is 0. Quick conclusion here. Two comments. One, we know because this limit exists, we know that y equals 0 is a horizontal asymptote. That's an immediate conclusion now. And other thing, if we check the limit as x goes to -infinity, nothing changes. This 1 over x still goes to 0. -2 over x squared still goes to 0. The x down here goes to -infinity. I have -2 divided by -infinity, still 0. Still a fixed number over some type of infinity, that's 0. So here, y equals 0 is a horizontal asymptote, and if we take the limit as x goes to -infinity, it does not change the answer. Okay, just FYI, it's important. I think you should separately sit down and think about, basically redo the problem. None of the steps change, but do it as x goes to -infinity, just to practice thinking about, So for this third problem, so in the first problem, the degree in the numerator and the degree in the denominator were the same. And so the answer was the quotient of the coefficients of the highest degree terms, 2 over -1. In the second problem, the degree in the denominator was greater than the degree in the numerator, so the denominator blew up to infinity faster, and so the entire limit's 0. In this third problem, the degree of the numerator, I picked it to be higher than the degree of the denominator. And I was sneaky, I wrote the highest degree term as the second term. So, one mistake you want to make if you're trying to use the shortcut formula, in this case, is to go, oh, this limit, I can just cut out these terms and the limit's 1. That would be wrong. The highest degree term in the numerator isn't x, so watch out for that. Okay, so let's do this. So things I'm noticing that I want you to notice. Number 1, this is a limit problem. Number 2, it's a limit as x goes to infinity. And number 3, I have a quotient of polynomials. So I know in that case, I only care about the highest degree term. So I'm mainly worried about -2x squared and x. And if you plug in infinity here, you get basically -infinity over infinity. Okay, so I've written it right here. So first, I put the highest degree term in front, because if I don't do that, there's a good chance I'm going to make a mistake. So here I put the highest degree term in front. Then I tried to plug in the infinity, and you get an infinity over infinity type. Really, it should be -infinity over infinity, but I'm just trying to save space. So there's an infinity over infinity type problem. And I know in this scenario, factor out the highest order term in the numerator and denominator. And then do the algebra. X squared and x, there's cancellations. In the denominator, I can completely cancel this x. In the numerator, I can cancel one of them. Now look what happens when we send x to infinity. 1 over x goes to 0. This entire numerator term, this part in the parentheses will go to 2. And this x right here is going to blow up to infinity. So we'll keep track of that here. So this x right here is going to blow up to infinity. So the numerator is going to -2 times infinity. So there's the infinity here, but don't forget the -2. So the entire numerator actually goes to -2 times infinity or negative infinity. In the denominator, 3 over x goes to 0 because x is blowing up. The numerator is fixed, the denominator is blowing up to infinity. So this 3 over x goes to 0. In the denominator, all we have is just the number 1. The only thing that survives is this number 1 right here. So this limit is negative infinity over 1. Or just negative infinity. So here I canceled. Now when you send x to infinity, here in the numerator, these two terms here go to negative infinity, the -2 times x. That goes to negative infinity. The plus 1 over x, that goes to 0. The denominator goes to 1. So negative infinity plus 0 divided by 1 is just negative infinity. So let me do this problem again using the shortcut. So I want you to do this, the shortcut. Once you do this technique a couple of times, it becomes tedious to have to do it every time. So that's why we have the shortcut. But that's after you first understand, the technique. So for the shortcut, I want to first have the highest degree term as my first term. So I'm going to do the shortcut here on this second step. So the shortcut says, because we're going to infinity and these are polynomials, let me ignore all of the low degree terms. I only care about the highest degree terms. So now I'm looking at the limit as x goes to infinity of -2x squared over x. Now let me simplify. So here in the denominator, cancel the x. In the numerator, cancel one of the x's. So if you look now, this is just basically the limit. So let me just get rid of this denominator because we canceled it. We get rid of this. So if you look now, this is just basically the limit of -2x as x goes to infinity. And because of the minus sign, the limit now will be negative infinity. We're just sending -2x as x goes to infinity. So yeah, the limit's negative infinity. So that means there's no horizontal asymptote, at least when we go towards infinity. I still need to check the limit as x goes to negative infinity. But look, when I send x to negative infinity, if we use the shortcut, the only difference here, so if you take a look, the only difference here, let me do the shortcut here. So here I want to look at 2x, -2x over 1, right? When you do the shortcut, everything cancels. So now, if I send x to negative infinity, so now here, send x to negative infinity. Because of this minus sign, minus times minus, this will go to plus infinity. So when I send x to negative infinity, the limit's plus infinity. So in both cases, so this says no horizontal asymptote when we head, to the left for the graph going to negative infinity. And this limit here, that was equal to negative, no horizontal asymptote when you head to the right. So the previous two cases, we did have a horizontal asymptote. And it was the same whether you went x to infinity or x to negative infinity. In this case, no horizontal asymptote. The limits are different. If you go x to infinity or x to negative infinity, the limits are different, but they're both do not exist. They both blow up, either blow up to infinity or blow down to negative infinity. So no horizontal asymptotes at all, which is fine. A function, may or may not have horizontal asymptotes. It's fine. We're just investigating whether it does or does not. So these three examples are really important because they have this dominance of power idea. And the main things for you to keep in mind is it's a limit going to plus infinity or minus infinity, involving a rational function, involving a fraction of polynomials. And in this case, we only care about the highest degree terms in the numerator and denominator. And using the highest degree terms, it's a shortcut called dominance of powers. We should be able to figure out the limits. Okay, so this is an important slide, and I'll have you, take a look at it on your own more carefully. So this next example is very, very sneaky. It involves my favorite absolute value function, which I love. And this is an example where you'll see the limit as x goes to infinity will be a finite number, but different from the limit as x goes to negative infinity, which will also exist, but will be a different number. Okay. So here, first of all, note the instruction says find the horizontal asymptotes. So I know by definition, that means we need to look at the limit as x goes to infinity of this function. And we need to check the limit as x goes to negative infinity. If either one of them exists, then there'll be a horizontal asymptote. In this case, both of them will exist and will actually be different numbers. I'll show you. So for the first limit, I'm going to start by looking at the limit of the function as x goes to infinity. So for this first limit, so I'm going to make some comments here that don't make sense right now, but they'll make sense when we start doing the math. So I want you to read these in 2 steps. So first, there's this first claim that I make, that if we're sending x to plus infinity, then we can assume that x is bigger than 0, right? Because it's going to plus infinity. X is really large. So we can assume x is greater than 0. And how will I use that piece of information? So you'll see I will use it when we come across an absolute value. So I'm claiming if x is going to infinity, then that means x is greater than 0. And then, we know the positive square root of x squared is actually the absolute value of x. But in this case, if x is greater than 0, then I can replace the absolute value of x with just x. Okay, so this will all make sense in 1 second. Let me do the math now. So these are all kind of preliminary comments, which we'll use here in 1 second. So let's try the limit. So I'm doing the limit of x over the positive square root of x squared plus 1 as x goes to infinity. Here, I only care about the highest order term in the numerator and the denominator. If you send x to infinity, we get the indeterminate form infinity over infinity. In this scenario, I know I've memorized the strategy is to factor out the highest order term. In the numerator, there's nothing to factor out because it's just a single term. In the denominator, I need to factor out an x squared. So x squared divided by x squared is just 1. And 1 divided by x squared gives us the second term here, 1 over x squared. And then we've got our x squared outside that we factored. And now some more algebraic simplification. I don't know if you remember this, but the positive square root, the root of a times b is equal to, and you can break this up, the positive square root of a times the positive square root of b. So you can break up a root in a product. The square root of a plus b in general does not equal the square root of a plus the square root of b. Okay, products and quotients you can break up under a root, but not sums or differences. So here, let me write this as positive square root of x squared times positive square root of 1 plus 1 over x squared. So we'll write that as 2 terms. Now you remember we talked about this. The positive square root of x squared does not equal x in general. The left-hand side here is always positive. We're talking about this expression here. That's why I'm not calling it the square root of x squared, right? The square root would be both roots. This notation specifically is only asking for the positive square root of x squared. So that left-hand side is always positive. So the positive square root of x squared in general is equal to absolute value of x, not equal to x. So that's what I do here. I replace this positive square root of x squared with the absolute value of x. Now I'm going to use this stuff. Now I'm going to say since x is going to infinity, x is positive. If x is positive, I can replace the absolute value of x with x. And that's what I do down here. So you should notice this absolute value of x now became x. Why? Because of this reasoning up here. Now we can cancel. Cancel, cancel. Now, and take the limit. In the numerator here, in the numerator, I have a 1. In the denominator, I have positive square root of 1 plus, and this term here, the numerator's fixed, the denominator's blowing up to infinity, this term goes to 0. So I have 1 over the positive square root of 1 plus 0. The answer is just 1 here. So y equal to 1 is a horizontal asymptote. Now, when I send x to negative infinity, the absolute value of x no longer becomes x. This part is going to be different when we send x to negative infinity, because when x is going to negative infinity, we can no longer assume x is positive, but when x is going to negative infinity, instead, what we can assume is x is less than 0. And you know that when x is less than 0, the absolute value of x equals negative x. So here, I'm following the same steps here. So now I'm doing the limit of this function now is x goes to negative infinity as opposed as x goes to infinity. It's the same steps. I'm going to factor out, in the numerator, there's really nothing to factor out. I'm going to factor out the highest term in the denominator. I'm going to break up the positive square root, the positive square root of the product is the product of the positive square roots, and I'm replacing the positive square root with an absolute value of x. So that's this step right here. I didn't want to rewrite everything. Now, because x is negative, I can replace that absolute value of x with a negative x, not an x. And now, we're going to cancel, numerator and denominator. In the numerator, I have 1. In the denominator, I have negative root 1 plus 1 over x squared. The 1 over 1 plus x squared goes to 0. So I'm just left with 1 over negative root 1. So my answer here, so my answer here is y equals negative 1. So in this case, the limit as x goes to infinity, if you look, was 1. This is x going to infinity. And the limit as x goes to negative infinity was negative 1. So not the same, be careful. It has everything to do with this absolute value. Here we have 2 horizontal asymptotes, y equal to 1 and y equal to negative 1. So let me show the graph. Let me just make a quick sketch here. The graph here looks something like, so let me put in the horizontal asymptote. Here's the horizontal asymptote. We'll use a different color. Here's the horizontal asymptote 1 at the top here. Here's the horizontal asymptote negative 1. And the graph looks like this. If you've seen the arctangent graph, this looks very similar to the arctangent, but it's not. So here, so this is 1 up here, our horizontal asymptote, and this is negative 1 down here. You can see as x goes to infinity, we have a horizontal asymptote up here of 1. And when x goes to negative infinity, we have this horizontal asymptote negative 1. And here, I want to do this example. It's a little strange. It's a little weird. Definitely, you know, this is a slide that is worth reviewing, especially this sneakiness here with the absolute value. That you should review what's the definition of the absolute value and what's going on there. Okay, so I want to do an example where the limits were not the same, but they existed. It's going to 1 in one direction, negative 1 in the other direction. All right, folks, so the very last indeterminate form that I want to talk about is the infinity minus infinity indeterminate form. Remember, infinity is not a number. Infinity is a behavior. Infinity is the behavior of getting larger and larger. So here, infinity minus infinity is an indeterminate form because we don't know which infinity is growing faster. Is this infinity here in the front, is this one growing faster? Is it blowing up faster? Or is this infinity here, the second term, blowing up faster? You know, what do I mean by blowing up faster? Think about the graph of y equal to x. When x goes to infinity, that goes to infinity. But compare it with the graph of y equal to x squared, right? That also goes to infinity, but much faster. And so infinity, there are different types of infinities that move at different speeds. There's y equal to x, and you compare it with y equal to x squared. Well, they're both going to infinity, right? They're both going to infinity as x blows up, but obviously one function is going to go to infinity faster. X squared is going to get there faster, you know? So when it comes to infinity, there are many different types of infinity, and that's why infinity minus infinity is a problem. We don't know, is one growing faster than the other? Are they balancing each other out? Like, what's actually happening? Okay, so that's why, you know, infinity minus infinity is an indeterminate form. However, infinity plus infinity is not an indeterminate form. If you say, oh, I have something that's growing out of control, added to something else that's growing out of control, yeah, well, combined together, they're still growing out of control. But infinity minus infinity, I don't know. Is one growing faster than the other? Are they growing at the same rate? So infinity minus infinity, you know, is an indeterminate form, okay? So in a limit, if you get infinity minus infinity, that's feedback that we need to try something. So let's look at this first example. I have the limit as x goes to infinity. So I want you to notice it's an infinite limit at infinity of root x minus x. If I just plug it in, obviously I get infinity minus infinity. And so this tells me, okay, hold on, indeterminate form. Hold on, we have an indeterminate form. And so we need to try some math strategy. In this case, given the form here, the trick is to factor out the common term, you know, and that's something we're always looking for. Just algebraically, that's something we should have noticed, that there's a common term that we can factor out. So here's my limit. I plug it in, I get infinity minus infinity. So let me factor out the square root of x. The common variable is x. We factor out the lowest power of the common variable. Here, x to the 1/2 is the lowest power. So remember, x divided by square root of x. So now we're dividing, right? So x divided by square root of x is 1. That's where this 1 comes from. And square root of x divided by square root of x is 1, and x divided by square root of x. Remember, that's x to the 1 divided by x to the 1/2. So that's x to the 1 minus 1/2, or just x to the 1/2, or root x here. And now we can take the limit. As x goes to infinity, this root x goes to plus infinity times, so maybe I'll put parentheses so you know it's a multiplication, okay, times this 1 minus root x, as x goes to infinity, goes to negative infinity. And this is a multiplication. Infinity times negative infinity, our limit here is negative infinity. It kind of makes sense because x goes to infinity faster than square root of x, if you think about the graph. So this kind of makes sense to me. that the limit here should be negative infinity. So here's another example. This is tricky. I want you to really pay attention here. Here, x is not being sent to plus or minus infinity. X is being sent to 0 from the right. Now, if you check here, what happens when I plug in? I get 1 over 0 in a limit that's plus or minus infinity, but x is approaching 0 from the right, so 1 over x is positive. So this first term is a plus infinity in the limit. Minus, so I'm going to copy the minus. This, when you do the limit, again, if you apply the limit, this is 1 over root 0 or number over 0. In a limit, we know this is going to be plus, in a one-sided limit, we know this is going to be plus or minus infinity. And 1 over positive square root of x, that's positive. So this second term goes to infinity. So this limit is an infinity minus infinity type indeterminate form. And I'm going to stop right here. I will continue with this example next time. Of course, you can read ahead and should, and I'll finish up this example next time. Thank you for your time, everybody. I'm going to stop right here.